So since we started looking for the convection diffusion problem, we were able to approximate both diffusion and convection by different schemes. Just to recap what we did again, in the diffusion term, we usually use the central differencing scheme to do that. When it came to the convection term, the first scheme that we covered was the central differencing scheme. Then the second one was actually moving to the upwind scheme. In the upwind scheme, just as a reminder, we assume that the function phi is constant within the cell, right? So we have, this is my present point, and I have an east face, and I have the west face, and I have the west node in here. And it depends on the flow direction. We indicate this direction is always a positive one. You could have the same situation in a negative flow. So in the upwind scheme, we assume that phi will change constant. It will be constant, there's no change, which means that we can predict the value of phi at the east face is the same as the value of phi of the upstream node. So if the flow is coming this way, this will be the upstream node. So this is going to be phi p, and this will be constant here. If we're looking for the west face approximation, phi of the west face will be simply the phi of the west node, since we are assuming it's constant phi function. If you're looking for the negative flow direction, this is the east node here. Now, for the east face, the value will be the same as the upstream node, which is phi east will be the same as phi east. And if you look to the west face, it will be the same as point P. The flow is going in this direction, so phi of the west face is the same as phi P. Upstream node is the same as a face. So this is what we did in the upwind scheme. In the quadratic upwind scheme, the approximation of the value phi, so in quick scheme, the value of phi at faces is estimated by constructing a quadratic equation in the form of phi change within the cell as ax squared plus bx plus c. And in this case, we will use using two upstream nodes and one downstream node. So this will give me 3 points, so I can construct that quadratic equation. Let's approximate that in a schematic here, which means that if I'm looking for, that's P, that's east, that's the west. We're looking for the approximation on the face, that's phi east, and that's phi west. And I'm going to assume that the flow is going into that direction. So if I'm interested to find the value of phi on the east face, I will pick two upstream nodes, which will be W and P. And I will pick another downstream node, which is E. Then I'm going to construct a quadratic equation, second order equation, using phi west, phi P, and phi east. Then when I know what does this equation looks like as a function of x, I'm going to actually substitute by the coordinate x of that phi east face. Then I will find the value of phi east. So for phi east, I will have P and W are the upstream nodes, and I will have E as the downstream node. If I'm looking for the phi of the west face, which is here, right? Now I'm going to need two upstream nodes. I'm going to need another node here. We call that second node is west of the west, WW. So if I want to do the approximation for phi of the west face, I'm going to need W and WW, west to west. This will present, these two nodes will present the upstream nodes, and P will be my downstream nodes. Some reference books actually call that for the east face, these two nodes surrounding that east face, sometimes they call them the bracketing nodes. And here for the west face, these sometimes called the bracketing nodes. So I have two bracketing nodes, and this will be upstream node, right? Two bracketing and upstream, then two bracketing and upstream. So different reference books describe it in a different way. Okay? Then that's for approximating phi east and phi west, and these two are for the convection term. If you recall, if you start from the general transport equation, you integrate over the volume of the cell, then use the divergence theorem to convert that into controlled surface approximation. Then you will end up having F east, phi east minus F west, phi west equal to kappa east, A east, d phi by dx to the east face minus kappa west, A west, d phi by dx on the west face. So I would say that the quick scheme, step number one is you have to use two upstream nodes and one downstream node. And you know that if I change the direction of the flow, you have to be careful where is the upstream and where is the downstream side. The other major step or a change between the quick scheme and the other schemes that we did before, it's actually impacting the diffusion term. So for example, when we do, so I will say this is the definition of the quick scheme. I will call that note number A. Note number B about the quick scheme. When you apply it, we usually have d phi by dx is defined on the east face or the west face. We didn't change that along the previous recordings. It's always coming from the central differencing scheme. So we usually have P, east, and the west. And if we're looking for the derivative at the east face or the west face, we assume linear change. This is phi east, this is phi P, and this is phi west. Then we can get d phi by dx on the east face by phi east minus phi P divided by this distance here, which is delta x east, and this distance here is delta x west. And d phi by dx in the west face will be phi P minus phi west over delta x west. Nothing changed here so far, right? But when we used to come near the boundary, if you guys recall that if this is a boundary node and I have a boundary here, we used to have, let's actually have that in a separate drawing. So this is great for interior nodes, correct? And this has happened all the time, whatever, regardless of what scheme we are using, right? That's always the same for the diffusion approximation. But when it comes to a boundary node, let's assume that we have a boundary here, and this is my P point. I have the west here. Now, this is my west face, and this will be my east face over that boundary. Or if we look into a left boundary node, this is going to be your P. This is going to be my east. The east face will be here, and the west face will be here. Okay, then we're looking for d phi by dx for this case here. I can get for the east face, and I need to get d phi by dx for the west face. Again, we assume the linear change, and let's call that phi b, and let's call that phi a. So here, this is phi b, this is phi p, and this is phi west. So if you want to get the slope d phi by dx on the west face, it's going to be phi p minus phi west divided by delta x west. So far, that's okay. But when it comes to the east, we used to say that this distance called delta x naught. So I would say that this is phi b minus phi p divided by delta x naught, right? If I look to this case here, this is phi east, this is phi p, and call that phi a. This is delta x naught, and this is totally delta x here, east, right? So we used to say, okay, d phi by dx on the west face is simply phi east minus phi p divided by delta x east. And for the west face, that's east, d phi by dx on the west. I think I'm a little bit tired here. So that's east and that's west. So d phi by dx in the west face will be simply phi p minus phi a divided by delta x naught. If the distance that you are using to calculate the diffusion approximation is not equal delta x east or delta x west, quick scheme does not allow for that, which means that this approximation and this approximation are not allowed in quick scheme. So now this is becoming a little bit more complicated now. So we can use this or this in the interior nodes, but when it comes closer to the boundary, we cannot use the approximation. This is not allowed. This is not allowed. There's an alternative way to do that, and we're going to explain that, especially when I go through an example to make it more practice and understand what's going on. So that's these are the two characteristics of the quick scheme. We use two upstream nodes, one downstream node, and the diffusion is okay to be used for interior node as long as the distance is a full still separating distance. If you come to the boundary nodes, that delta x node approximation, it's not going to work anymore. And we will see how to deal with that when we go to the example. So now let's see how we're going to actually drive that quadratic equation as described in the quick scheme description. So I'm going to have node P, node E, and node W, and I would use that phi west, phi P, and phi east values. Then I'm going to construct a second order equation here. Then after I have this equation, I will find the coordinate of the east face. I will find the coordinate of the west face. Then I will find what is phi east and phi west from this quadratic equation. So in a simple way, let's assume this is interior node like P here. I'm going to start proposing a x coordinate system. I'm going to say that I'm going to put my x coordinate system starting from here. That's x. So for this location here, x is equal 0. For this location here, x is equal delta. Let me review that. So that's delta, right? Measure from here. Then I would have this is also another delta. So that's now 2 delta, right? And this location here is delta over 2, and this is 3 delta over 2. I'm just putting the x coordinate for each point from that reference coordinate system axis here. So phi as a function of x will be a x squared plus b x plus c. Then I have at x equal 0, phi at that value is equal to phi west. At x equal delta, phi at x equal delta is simply phi p. Then the third condition is at x equal 2 delta, I say that phi of x at 2 delta is simply phi east. three conditions, three boundary conditions, I can simply get my A, B, and C. So let's substitute here. I'm going to put x equals 0, 0, 0, phi is equal phi west. So I got C is equal phi west. That's my first coefficient. Let's go for the second coefficient, which is x equal delta. I will replace phi by phi p. So phi p is equal A delta square plus B delta. And I got C equal phi west. I will go with the third equation. X will be replaced by 2 delta, and phi will be phi east. So phi east is equal A 2 delta square plus B times 2 delta plus phi west. You can solve these two equations together, so you can get the value of A and B. I got A is equal to phi west minus 2 phi P plus phi east divided by 2 delta, and I got B is equal to 4 phi P minus phi west plus 3 phi east over 8. Now I can take the A, B, and C and go back to the quadratic equation so I can have that quadratic equation fully constructed. If I do that, I will get the equation in that format, that phi as a function of x is equal to, and actually remove this, is going to equal to phi west minus 2 phi p plus phi east divided by 2 delta. That's multiplied by x squared plus 4 phi p minus phi west plus 3 phi east divided by 8 times x plus phi west. I got my quadratic equation. Now I need to get the value at the east and west face. If I go back to this diagram, the coordinate of the west face is delta over 2, and the coordinate for the east face is 3 delta over 2. So I'm going to substitute into this equation. If I want to get phi on the west face, I will put x equal to delta over 2. If I want to get phi on the east face, I will put x equal 3 delta over 2 in this equation. So now you will find yourself, you got phi east is 6 over 8 phi p minus 1 over 8 phi west plus 3 over 8 phi east. And you'll find also that the value of the phi west is equal to 6 over 8 phi west plus 3 over 8 phi p plus minus 1 over 8 phi ww. So if I go back, this is P, this is E, this is W, this is WW. I'm looking for the phi of the west face and phi of the east face. I'm looking now for the positive flow direction. So you find that phi of the east has 2 upstream nodes, P and W, then 1 downstream node, which is E. If you look to the west face, I have 2 upstream values, W and WW, and I have 1 downstream node, which is P. You can imagine if the flow going into the other direction, what would it change into this equation, right? And we can actually drive a general format for phi on any face, east or west. So that face could be east or west, right? Is equal to 6 over 8 phi I minus 1 plus 3 over 8 phi I minus 1 over 8 phi I minus 1. This is the general form for phi. How you define I minus 1, I minus 2? So let's assume this is your P point, right? So my this is the east face, right? So I will call this as I minus 1, I minus 2. So if you substitute here, you will have 6 over 8 phi P, so which is here, 3 over 8 phi I, which is 3 over 8 phi east, according to this I here, minus 1 over 8 phi I minus 2, which is west. If you apply this to the west face, in the west face, this will be my I, this will be my I minus 1, this will be my I minus 2. So if you look to the west face, you will have 6 over 8 phi I minus 1, which is phi west, which is the first term. Then 3 over 8 phi I, 3 over 8 of phi p, 3 over 8 of phi p, minus 1 over 8 I minus 2, which is 1 over 8 W is T. So this is the general form to get the value of phi east and phi west. Now you can go back into the general equation, F east phi east minus F west phi west equal kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face. Again, I would assume so far that we are looking for interior nodes, so I can actually use the approximation for the diffusion. So I'm going to say that for interior nodes, which means that exclude boundary nodes. Okay, that's excluded. So I'm going to just looking for the interior node. So I can now fill the big equation here and see where we're going to go. So I'm going to go with F east, phi east, I will substitute with this term here. So I'm going to have 6 over 8 phi p plus 3 over 8 phi east minus 1 over 8 phi w. Okay, and minus F west, phi west will be 6 over 8 phi w plus 3 over 8 phi p minus 1 over 8 phi ww. It's equal to kappa east A east. Again, I'm looking for interior nodes, so d phi by dx in the east can be simplified by phi east minus phi p divided by delta x east minus kappa west A west. That's going to be phi p minus phi west divided by delta x west. Now I can collect the term. We know that d is actually kappa A over delta, and I know that that's going to be east is going to be d east, and the same will be for the west. So the equation can be approximated as the following here. I will collect the term, so I will have d west plus 6 over 8 f west plus 1 over 8 f east plus d east minus 3 over 8 f east minus 1 over 8 f west plus f east minus f west. That total terms multiplied by phi p, it's equal to d west plus 6 over 8 f west plus 1 over 8 f east plus that's phi west plus d east minus 3 over 8 f east, that's multiplied by phi east minus 1 over 8 f west phi ww. So now I can look to the coefficient here. So this is simply A west. This is simply A east. This is simply as SU. This is again as A west. This is A east. And the combination of these two terms here is minus SP. We know this is going to end up to be 0 for the continuity equation, but that total term here is my AP. So the final form of that equation coming from the quick scheme is simply AP phi P equal A west phi west plus A east phi east plus SU, which is the standard format of the equation. What's different from every time we use different scheme, the coefficients are different. So now A east is D east minus 3 over 8 F east. A west is D west plus 6 over 8 F west plus 1 over 8 if east. I got SU is equal minus 1 over 8 if west pi west west. I got my SP is equal where's SP? My SP is, oh, actually, this is actually not SU here, right? This is, let me double check that for a second. Yeah, if you put it that way, it's going to be SU, but I think we can also put that in the form of AWW phi WW, right? So this means that I will have, this is going to be actually not SU, that's going to be up to here. This will be the AWW, right? Let's write down that in red text, AWW. So now I'm getting AWW. Let's write that AWW is minus 1 over 8 if west, right? So now in this case, SU will be 0. That's, I can cancel that term. And what else? I can get my, that's going to be AWW now. That's not going to be SP. SP is going to be only here. So that's going to be AWW. I think that's more generic format here. So we got AWW. So my SP is actually equal minus, it's going to be FE minus FW, which I know it's 0. And now AP will be AW plus A East plus AWW plus 0. So that's going to be the final term here. So actually, SU will be actually 0. That's correct. Okay. So that's for positive flow direction. If you do negative flow direction, you maybe get different coefficient. So that's for positive flow. If you want to go for the negative flow direction, for negative flow direction, I will get the following equation here. I will get AP phi P equal to A East phi East plus A West phi West. Now you are getting this. This is my P. This is my flow direction, negative flow direction. This is the east point. This is the west point. Now I need 2 nodes in the upstream. So I'm going to need east-east point, right? And this is phi east, and this is phi west, right? So I will have A east-east, phi east-east, right? Then you're going to have A east is simply D east minus 6 over 8, F east minus 1 over 8, F west. You will get A west is equal D west plus 3 over 8, F west. You will get A east east equal 1 over 8, F east. Then I will get AP, it's simply equal A east plus A west plus A east east plus the FE minus F west, which is actually 0. And SP also is going to be 0, and SU is going to be 0. SU and SP maybe have a value if you have a source term, but we don't have source term in that part here. So that's in a simple language here what the quick scheme is, how you apply the quick scheme. And now we are having more added coefficient, A east east, A west west, into that application. So that's conclude the quick scheme. And I think the next logic step is to have an example and go through it. It's important when you actually deal with, actually let me cover that here before I leave. What about, we mentioned the approximation. So for interior nodes, we agreed that for the diffusion term, I can use this approximation, either west or west, east or west. I'm going to use phi minus phi over delta x, either east or west. But we said that situation is not going to be valid in the quick scheme when the node comes closer to the boundary. So let me explain how you're going to approximate the diffusion term in the quick scheme when the point coming close to the boundary. So let me propose here. That's a one-dimension domain here. That's a boundary face here. Let's assume this is my P node. This is my west node, and I'm looking for diffusion right now. I'm looking for the diffusion term. The second case, I will be here. That's going to be my P, and that's going to be my east. We know that this distance is delta X node, and this is delta X. Same, this is delta X node, and this is delta X. And we're going to call that phi B, and we're going to call that phi A. Now, I need to get d phi. Now the east face is going to be here for the node B. That's east face. West face has no problem. Now this is going to be the west face, and the east face here has no problem. So d phi by dx on the west face, it is very easy here. That's phi p minus phi west divided by delta x west. Done. Here, d phi by dx on the east face is simply phi east minus phi p over delta x east. No problem if you have a distance full delta x, right? The problem is when you have delta x node and when you have delta x node. So the quick scheme is proposing the following, is to construct a new quadratic equation between phi b, phi p, and phi west. So I will derive phi as a function of x equal ax squared plus bx plus c using phi b, phi p, and phi west. Then when you got this equation, you need to get d phi. I need to get d phi by dx on the east face. That's what I'm looking for here. I couldn't use the linear approximation because of delta x node. In this case, I will derive also the quadratic equation between 3 points, which is phi a, which is a boundary condition, phi p, and phi east. So now I will get ax squared plus bx plus c. I'm doing them side by side so you can understand what we are doing. Here, I'm going to use phi p, phi b, phi p, and phi w. Here, I'm going to use phi a, phi p, and phi e. Again, to construct the quadratic equation, I'm going to initiate an x-axis. Now I have x equal 0, right? I know that phi at x equal 0 should equal phi a. Now at x equal delta over 2, phi at x equal delta over 2 is simply phi p. At x equal 3 delta over 2, right? That's half, that's a full, because we know delta x node is half delta x, right? Phi at x equal 3 delta over 2 is simply equal phi east. 3 boundary condition, I can get a, b, and c. Here at x equal, here I'm going to set up the x coordinate like this. I'm going to start from here. This is my x coordinate. So x equals 0 here. X equal minus delta over 2 for the point P, and x equal minus 3 delta over 2 for that depth. So x equals 0, and phi at x equals 0 should equal phi b. At x equal minus delta over 2, phi at that location is simply phi p, and at x equal minus 3 delta over 2, phi at x equal minus 3 delta over 2 is simply phi west. Now, 3 boundary condition, I can get the 3 one. Which one I'm interested in? I got that function or I got that function. I'm looking for d phi by dx on the east face for this side. Here, I'm looking for d phi by dx on the west face for that side. I need this because I couldn't use the linear approximation here as well. So, you got this equation, take the derivative. So, d phi by dx is equal to 2ax plus b. Do the derivative here. D phi by dx is going to be 2ax plus b. Now I need to get d phi by dx at the east face. What is the x coordinate for the east face? Is x equals 0. You put x equals 0 here, so d phi by dx on the east face you're looking for is actually the coefficient b. You do the same here. I want to get d phi by dx on the west face. What is the x coordinate of the west face? I started from here, so x is equal to 0. So d phi by dx on the west face is simply b. So all what you need to do is to find the coefficient b of this quadratic equation, and this will give you the approximation of the diffusion term when you are near boundary, physical boundary of the domain. This is very important. This is the exceptional step from all what we covered before. We use the central differencing scheme for convection. We use central difference scheme for diffusion. When we went to the upwind scheme for the convection, we did not change the central difference scheme for the diffusion. It's always linear, linear, linear. But now, since we upgraded the convection term to a quadratic, it's also allowing us, or it's forcing us to upgrade the diffusion near the boundary to be quadratic as well. So this is a second major difference in the quick scheme. That's for the diffusion term near the boundaries. And the second difference is the how we approximate the diffusion term by phi phase for the east and west one. So that's conclude actually the quick scheme. And again, the example will highlight all these activity with numbers as we go. Let's conclude that recording.